Coming back to understanding what really sets the resolution of a telescope in practice, we've seen that theoretically it should just be about the diameter or the aperture of your telescope and the wavelength or frequency that you're observing. We've seen that specifically, if you want to estimate the size of a telescope, the diameter that is required to get some sort of resolution in arcsecond, we can use this formula. So we re-express this to get the angle in arcsecond, and lambda being in the same units as d. But let's look at some practical examples. Behind me, you can actually see this side and this side. They're images that were observed within minutes at exactly the same wavelength. And if you look carefully, you will realize that these images are showing exactly the same sources. It may not look like this at first sight, but if you look carefully at it, you'll be able to identify pretty much all the sources from this side. And for example, you can see this star over here is shown here. And these two stars, actually, you can see very clearly as two stars in this image. Then it starts to be very blurry. What you're seeing is the consequence of imaging things with some poor resolution of something like 3 arcsecond versus something that has a much higher resolution of 0.9 arcsecond at this wavelength. Of course, if you were to take the theoretical formula into full consideration and explain the differences simply as a difference in diameter, you'd probably conclude that this image was taken with a telescope of about 5 centimeters, and this image would have been taken with a telescope of 15 centimeters, something like 3 times larger. Is this really the case? Now, if you've seen the lecture notes, that's sort of cheating, and you've probably realized already that it is not the case. These two images were actually done with exactly the same telescope, the same exposure time, and the big change were the actual atmospheric conditions. As we'll see next, this image was done with very poor seeing, where the atmosphere was quite turbulent, and for this image, the atmosphere became slightly more stable, and therefore we ended up having a sharper picture. Therefore, the question is definitely not whether this image was taken with a 5 centimeter telescope and this one was done with a 15 centimeter telescope, but rather what happened to the light before it actually hit our telescope and detector. Now, the greatest limitation to telescopes operating from the ground is something called seeing. The seeing is a delta theta that will be the limit of your resolution typically. Seeing is actually caused by turbulence in the atmosphere that makes it act essentially like a medium whose refractive index is changing all the time. And therefore, the light of a star that would actually come as a straight line and just produced a point-like image on the ground will not do that, because these light rays will be refracted all the time. What really happens is that the star is still hitting the ground as a point source, but it's because of the way that light is actually shifted a little bit spatially. It is hitting the ground at slightly different positions. This is very fast. I mean, we cannot see it with our own eyes, but if we were to do exposures, really, really short ones and very fast, we would see that the star is actually hitting the ground at different positions. And therefore, whenever we capture things with a few seconds or even with the time that it takes for our eyes to form an image, what we'll see is not a point-like source, but actually something that's blurred. The higher the seeing, the higher the turbulence, essentially, the more the light rays will be refracted, and therefore the larger the seeing. And the way we measure seeing is actually by measuring the full width half maximum of what otherwise would be a point-like source. So if you're looking at a star through a telescope, or you take a photograph, or you expose it in a CCD, as we shall see, you're doing it for a certain amount of time. And what you can do is, for example, slice away spatially in terms of angular position and measuring the flux of the star. You will peak at some maximum, let's call it 1. And what we measure as seeing is essentially the angular separation between the 50% of this flux at the peak. This is what we call seeing. We can also see it on this side, that we have a star that at the diffraction limit would have the size given by the resolution of a telescope. Once it goes through the atmosphere, it will actually be hitting different positions. So at any instant, if we were to be able to do like an instantaneous exposure, we would still see it as a diffraction limit size, but that is just not possible to do it at that short amount of time. Even a split of a second will be enough for this to be created. And therefore, at the end, what we have is some sort of blob. The size of this blob from the 50% from one side to 50% compared to the peak of the flux is what we call seeing. It is quite important to point out that at sea level, this limits the resolution to always around something like 1 to 2 arcsecond. And if you go to really high places where the atmosphere is incredibly stable, some of the sides include, for example, Mauna Kea, you can very easily get to something like 0.3 to 0.4 arcsecond. And some of the other places that are really good, you can get to something like 0.7 arcsecond. What does this mean? It means that a star that otherwise would be a point or point-like, when you actually image it, it will have a size from 50% to 50% of the peak that will be about 0.7 arcsecond, in this case in La Palma. It's also important to point out that the resolution of a telescope can actually change if you actually change the focal length. And sometimes telescopes will have instruments in different focus so that they can take advantage of different resolutions and magnifications. What always happens is, typically, if you're looking at a small focal length, that allows you to have a really large field of view, as you can see here. But that typically also means you have some poor angular resolution. Therefore, when you look at these wide fields, it's very difficult to distinguish sources like this. They will look like one. What you can do typically is, sometimes on the same telescope, or if you change the optics, you can use a larger focus. And with a larger focal length, you typically get a smaller field of view, for example, the one here on the reds, but that gives you higher resolution. So you can now actually study the details and distinguish this source as actually two, or for example, a binary of stars. We won't be discussing this in Physics 263, but just in case you encounter this F number, the focal ratio, is essentially defined as the ratio of the focal length to the diameter of the lens. This is not so important unless you start designing telescopes or you want to buy one, but it is important to understand one of the big limitations of refracting telescopes.